Let's look at the math behind this conservation of momentum idea. Conservation of momentum says that when you have a system of two or more objects and forces are exerted between these objects, then the total momentum of the system is conserved. Even though the momentum of each object is going to change, the total net change between the two is going to be zero. Now, a way to look at that is if I have cart 1 and cart 2 and they collide. When one hits 2, there will be a force exerted back on it. We're going to call this force of 2 on 1. And then cart 1 will exert a force on cart 2, which I'm going to call force 1, 2. Now, according to Newton's third law, the force between these two objects has to be equal and opposite. So I can say that force 1, 2 equals minus force 2, 1. Now, if we think about the impulse and momentum theorem, we know that the force times the time equals the change in momentum. So the force of 1 on 2, if I multiply it by the time, is going to be equal to mass 2 times the velocity of 2 final minus the velocity of 2 initial. And the force of 2 on 1 times time equals mass 1 times v1 final minus v1 initial. Now these are equal and opposite. I can assume that the times have to be exactly the same, because I can't imagine an object touching another object for a different amount of time than that object touches it back. So we have to assume that those are the same. So what I can do then is set the right-hand side of both of these equations here equal to each other, but I'm going to have to change the sign of one of them. So I'm going to say F1 on 2 equals minus F2 on 1. Now if I do all the algebra here, I'm going to get M2 V2F minus M2 V2O equals minus M1 V1 final plus M1 V1 initial. If I group this so that everything that is initial is on one side and everything that's final is on the other side, I'm going to wind up with mass 1 times its initial speed plus mass 2 times its initial speed equals mass 1 times its final speed plus mass 2 times its final speed. This is a statement of the conservation of momentum. What this says is that the total momentum before the interaction equals the total momentum after the interaction. And like the other conservation law that we learned so far, which is conservation of energy, you can apply this to a lot of different situations. The first specialized situation I want to apply this to is something called a recoil problem. And a recoil problem looks like this. It could be, say for instance, I have a cannon. And my cannon is loaded up with a cannonball, and we're going to fire it. But we haven't fired it yet. So I can say that the total momentum of the cannon and the cannonball right now are 0. So if I go up to my equation up here, since both velocities are 0, my total momentum before I fire this is 0. Now afterwards, the cannon is going to recoil backwards, and the cannonball is going to fly forward. And I can say that the mass of the cannon times the speed of the cannon equals the mass of the ball times the speed of the ball. Now you can see the only way this is going to work out mathematically is if one of these terms is positive and one of these terms is negative. They have to add up to 0. This makes sense. Velocity is a vector. One of these velocities is going to be in the positive direction and one's going to be in the negative direction, and they are going to move away from each other. So this formula can be generalized to say that the total momentum before is 0 equals the total momentum after, which still has to add up to 0, but the individual speeds will not be 0. So this is your recoil situation. And this also applies to, for instance, a person standing on a skateboard, throwing a bowling ball. Anytime you have two objects that are together and motionless and then are pushing off one another and moving away from each other. Second situation is known as an inelastic collision. Inelastic collision is when two objects come together and then stay together. A typical example would be a railroad car that is moving and comes upon another railroad car. And in this case, I could say it's not moving. It doesn't matter if it's moving or not, as long as they come together. They could be moving, the one in front could be moving at a slower speed and is overtaken by the one behind, or it could be moving in the opposite direction. In any case, the thing that's important is that they're going to hit and stick. I'm actually going to say, let's say for instance that these things are moving towards each other. That way I can say that the second one does have momentum. I'm going to call this 1 and call this 2. So the momentum before the collision would be m1 v10 and m2 v20. That's the total momentum before the collision. Now, what makes it inelastic is that they're going to hit and stay together. What that's going to look like is going to depend on the momentum of the two objects. If object 1 has more momentum than object 2, when they hit and stay together, these objects would move to the right. If object 2, in this case, is moving to the left and it has more momentum, and they hit and stick, then these objects will move to the left. Another example of this would be in football when a tackle's made. The direction of motion after the tackle will be in the direction of the greatest momentum. So that's why it's important, if you're a football player, to try to build up as much momentum as possible before you make a tackle, and that way you can make sure that the motion after the tackle is in your direction, that you're moving instead of the opposite direction. When these objects hit and collide, and no matter what direction they wind up moving, and we're going to say they coupled and stayed together, what you can do to simplify the right-hand side of this is recognize that they are sharing the same speed. So I can find their total momentum just by adding their masses and giving them one common final velocity. So this is a formula that you can apply to any inelastic collision. Sometimes I call this the hit and stick collision. Now the third type is the free-for-all. It's called at least a partial, if not totally inelastic collision, and that's when things bounce off each other and go their own separate way. In that case, you just refer back to your initial equation right here, because that's the equation that takes in everything into account, and you really can't simplify it. In that situation, in order to solve for anything, you need to know all the variables except one. So you'd have to know both masses and 3 of the speeds, or all 4 speeds and 1 of the masses. But you get the idea. You're going to have to know a lot of stuff in order to make this happen. What's important when you do these type of problems is that you keep your information organized. One of the things that I tend to do when I do a problem like this is I make a chart off to the left, and I try to put in all the information that I possibly can, so I don't wind up putting numbers in the wrong place. That's what's going to sink you on problems like this. So it's not a bad idea to keep these things as organized as possible. And remember, you have to match up the correct speeds with the correct objects. So if you're told that you have, for instance, the cannon and the cannonball, you have to make sure you put the velocity of the cannonball with the mass of the cannonball and the velocity of the cannon with the mass of the cannon. If you don't match those up correctly, you'll get some funny results, and I'm sure that sounds like common sense, but it is one of the most common mistakes I see happening in a problem like this.